Chemistry lecture number 44, Balancing Chemical Equations. Substances react with other substances to make new substances. For example, gaseous hydrogen molecules will react with gaseous oxygen molecules to make water vapor. Below are Lewis structures of hydrogen, oxygen, and water molecules. We start with hydrogen and oxygen. The atoms then rearrange themselves to form H2O. So if you look at this, one of the oxygens from here will combine with these two hydrogens here to form one water molecule, and then this oxygen will combine with these two hydrogens to form the other water molecule. Now, instead of drawing Lewis structures to show a chemical reaction, we can write a chemical equation. Now, in the reaction, two hydrogen molecules react with one oxygen molecule to produce two H2O molecules. And the equation for this reaction is 2H2 plus O2 gives 2H2O. And if you look at why we're doing it this way, this Lewis structure is represented by the formula H2, and there are two hydrogen molecules, so that's why the number 2 is in front right here, and this 2 is called a coefficient. This Lewis structure for an oxygen molecule is represented by the symbol chemical formula O2. There's one oxygen molecule, so implicitly there's a 1 right here. Here's the Lewis structure for water, and then there are 2 water molecules, so that's why there's a 2 in front of the H2O right here. Now, hydrogen gas and oxygen gas are the reactants, and reactants are the substances you have before the reaction occurs. And they're also the substances that are to the left of the arrow. All right. The H2O molecules are the products of the reaction. Products are the substances you end up with after the reaction has occurred, and the products are always on the right side of the arrow. Now the G right here next to each substance indicates that the substance is a gas. Different physical states have different different notations. So all three of these are in the gaseous state. So all three of these have the letter G next to them. But what if they were liquids? What if they were solids? Well, below is a list of the notations used for different states of matter. So G is gas, L is liquid, Cr is crystal or solid, S is solid. AQ means aqueous, and that means that the substance is dissolved in water. Your textbook will include notations next to formulas, but I won't always include them in these lecture notes. So look at the equation below and see if you can detect what's wrong with it. If you look at it carefully, you'll see the equation is not balanced. There are an unequal number of atoms on each side. And the law of conservation of mass states that the number of atoms that exist before a reaction has to equal the number of atoms that exist after a reaction. So let's take a look at this. If you count the number of atoms on each side, you'll find that there are 3 carbons on the left, so C3, but only 1 carbon on the right. Just that 1 carbon right there. There are 8 hydrogen atoms on the left, but only 2 hydrogens on the right. So H8, 8 hydrogens here, and then H2, 2 hydrogens on the right. And finally, there are 2 oxygen atoms on the left, but 3 oxygens on the right. So the equation as a whole is unbalanced. O2, 2 oxygens right here, and then 2 oxygens plus 1 oxygen gives me 3 oxygens. So we have 3 oxygens here and 2 oxygens there. So the equation is unbalanced. So here are the guidelines for balancing a chemical equation. Balance equations by putting the appropriate number in front of the chemical formula. The number in front of the formula is called the coefficient. Never balance by changing or adding numbers to the lower part of the symbol. For example, changing H2O to H2O2 would be wrong. You just can't slap the subscript 2 onto the oxygen. Changing H2O to H3O would also be incorrect. Try to balance the complicated molecules first, balance the uncombined elements last. In general, we want the smallest whole numbers as coefficients in the equation. Now, there's no specific procedure for balancing equations. A lot of times you make a guess and hope that you're on the right track towards the correct solution. Let's balance this equation right here. We'll start with a guess and put a 3 in front of the CO2. And we do that because we have 3 carbons now, the 3 is distributed, and 3 here, C3, so the carbons are balanced. Next, let's put a 4 in front of the H2O right here. So if I do that, see we have 8 hydrogens right here. If I put a 4 right there, 4 times 2 gives me 8 hydrogens right there. So the hydrogens are now balanced. Now let's count up the oxygens. We have 2 oxygens right here, and then how many oxygens do we have right here? Well, 3 times 2. 3 times 2 gives me 6 oxygens right here, and then 4 times 1, so 10 oxygens. So there are 10 oxygens on this side of the equation right here. So to balance the oxygens, I'll put a 5 in front of the O2. 5 times 2 gives me 10 oxygens, and there's our balanced equation. All right, so there are now 3 carbons, 3 here, 8 hydrogens, 8, 4 times 2 is 8, and then 10 oxygens on each side of the arrow. 5 times 2 is 10, 6 plus 4 is 10. Now fractions such as 1/2, 3/2, 5/2, and 7/2 can sometimes be used as an intermediate step in balancing uncombined elements. Let's balance this equation right here. If you look at it, we've got 1 sodium on each side, Na and Na. There's 1 oxygen on each side, so oxygen here and oxygen here. So the sodiums and oxygens are balanced. But we have 2 hydrogens right here, and then 3 hydrogens right here. See, there's a hydrogen here, 1 hydrogen plus 2 hydrogens. So 3 hydrogens here, 2 hydrogens here. Hydrogens aren't balanced, but the sodiums and the oxygens are. How can we balance the hydrogens without messing up the sodium and oxygen atoms, which are already balanced? Well, if I put a 1/2 in front of the H2, we would then have 1 hydrogen plus, and then 1/2 times 2. So 1/2 times 2 gives me, 1/2 times 2 is 1. So that's going to give me 2 hydrogens. So you'll have a total of 2 hydrogens on this side if I put a 1/2 in front right here, and then we have 2 hydrogens right there. So now the equation is balanced. 1 sodium, 2 hydrogens, 1 plus 1, because 2 times 1/2 is 1, so we have 2 hydrogens here, so it's balanced. Now, if we don't want fractions on our equation, we can get rid of them by multiplying the coefficients in front of each substance by 2. So 2 times 1/2 is 1, so we'd end up with a 1 in front of here. So let's do that. So I'm just going to multiply all the coefficients in front of here by 2 and rewrite it. Implicitly, there's a 1 in front of the Na, so that's going to be 2 times Na, plus implicitly a 1 in front of the H2O, plus 2 times H2O gives me 2 times the 1 in front of here, 2 NaOH. And then 2 times 1/2 is 1, so that's just going to give me H2. Implicitly, there's a 1 right there. So this top equation right here is also an acceptable balanced equation. So if you want whole number ratios, this is what you get. 2 sodiums, 4 hydrogens, 2 times 2 is 4, and then 2 plus 2 gives me 4 hydrogens on this side, 2 oxygens, and then 2 oxygens here, so the oxygens are balanced. So each side now has 2 sodiums, 4 hydrogens, and 2 oxygens. Let's try balancing this one. So let's balance the carbons by putting a 2 in front of the CO2. If I do that, 2 carbons, 2 carbons. I can balance the hydrogens by putting a 3 in front of the H2O. I've got 6 hydrogens right here. Put a 3 there. 3 times 2 gives me 6 hydrogens. And then there are now 2 carbons and 6 hydrogens on each side. The right side has 7 oxygens. 2 times 2 plus 3 times 1. That's going to give me 4 plus 3. That's going to give me 7 oxygens. All right. So how can I balance the oxygens on this side? Well, if I put 7/2 right there, that will give me 7 oxygens on this side, because 7/2 times 2 gives me 7. So the equation is balanced if we want to leave it like that. If we don't want to have fractions, we can multiply the whole thing by 2. So 2C2H6. So 2 times, implicitly 1 gives me 2 there. And then 2 times 7 halves gives me 7. So this will become 7O2. Gives me, and then 2 times CO2. So that's going to be 4CO2. Multiplying all the coefficients by 2. 2 times 3 is 6. And there's the balanced equation without fractions. If you do it this way, you're going to have 2 times 2, 4 carbons here, and then 2 times, 4 carbons right there also. 2 times 6 is 12 hydrogens, and then 6 times 2 is 12 hydrogens. 7 times 2 is 14 oxygens, and then 4 times 2 is 8, plus 6, and that'll give me 14 oxygens on this side right here also. And the least common multiple between coefficients can sometimes be used to balance equations. So let's try to balance this one. If you look at this, we have 3 chlorines on the left and 2 chlorines on the right. And the least common multiple between the numbers 2 and 3 is 6. So what we can do is if we put a 2 here and a 3 here, that's going to give us 6 chlorines on both sides. 2 times 3 gives me 6 chlorines. 3 times 2 is 6 chlorines. So my chlorines are now balanced. And now we can balance the calcium and the aluminum. I've got 2 aluminums on this side, so I'll put a 2 right there. I have 3 calciums on this side. I'm going to put a 3 right there. So it's balanced now. Now if the equation has identical polyatomic ions in the reactants and products, treat the polyatomic ions as though they were elements. So let's try to balance this one. You notice that there's a polyatomic right here, nitrate, and the same polyatomic on the other side. So since we have the same polyatomics on both sides, we'll treat this as though this were an individual element. Now let's see, I've got 2 NO3s on the left and 3 NO3s on the right. So the least common multiple between the numbers 2 and 3 is 6. So least common multiple of 2 and 3 is 6. So what I'm going to do is I'll put a 3 right here, and that'll give me 3 times 2 gives me 6 nitrates. And if I put a 2 there, 2 times 3 gives me 6 nitrates on the other side too. So my nitrates are balanced. And then we can balance the other ones. I've got 3 coppers right here, so I'll put a 3 right here. And then I've got 2 aluminums right here, so I'll put a 2 right there. My aluminums are balanced. And also, you could say that there are 6 nitrogens on each side. So if you want to treat these as individual atoms, it adds up. 2 nitrogens times 3 gives me 6 nitrogens on this side. And then 3 nitrogens times 2 gives me 6 nitrogens on this side. And then if you want to balance the oxygens, 2 times 3 is 6, and then 6 times 3 is 18. So I've got 18 oxygens on this side. And then 3 times 3 is 9, and then 9 times 2 is 18. So we have 18 oxygens on this side right here too. All right, so that's how you do it. For a PDF transcript of this lecture, go to www.richardlouis.com. This has been Chemistry Lecture number 44, Balancing Chemical Equations.